Gluscevic, no? How should I do that?
Gluscevic, yeah.
Gluscevic. Who will be talking to us about the universe we cannot see. Sounds exciting.
All right.
Thank you, Vera.
Thank you, Susan. Thanks for having me. Thanks for sticking around in the afternoon. So for centuries, we used to look up at the night sky and call that astronomy or cosmology, the study of the universe as a whole. But now we know that every single thing we've ever interacted with, the stars, the planets, the gas, anything that we can see, and also anything that we can feel here on Earth, and everything you've ever heard about in particle physics amounts to maybe 5% of everything that there is in our universe. And in particular, we now know that the particles that we call matter and describe in fundamental physics theories constitute only 15% of all matter in our universe. And if we had the eyes to see the rest, this is more how our universe would look like. And you see that recognizable web of structure, the cosmic web. And most of that stuff consists of something we don't yet understand on the fundamental level. And we call it dark matter for the lack of better word. So I divided this talk in a few parts. I won't tell you how many yet. But I want to start with the story of how we came to understand that this is what our universe is like, that most of it is invisible and untouchable to us. And the story starts in 1970, and actually a little bit before that even. But in 1970, this astronomer, Dr. Vera Rubin, presumably on a dry, hot night at Kitt Peak Observatory in Arizona, relatively close to Tucson, mounted a brand new spectrograph that her colleague, Kenneth Ford from Carnegie Institutions of Washington, had recently designed. And she decided to point it to one of the nearby galaxies, the Andromeda Galaxy, which, by the way, is visible with the naked eye, even if you go to the mountains here, near LA. And Andromeda, we now know, kind of looks like the Milky Way. So it's like the big sister of the Milky Way. You can think of it that way. And what Dr. Rubin decided to do is, instead of taking a picture like this one of Andromeda Galaxy, she pointed the spectrograph to various positions across the disk of Andromeda. These positions are denoted in this plot from her seminal paper from that year. And the spectrograph had the capacity to take the light from the galaxy and kind of like a prism, split it into colors and then record it on photographic plate. And so the reason we do this kind of thing in astronomy is because once we break down light into the spectrum of radiation, what we can do is we can look for emission lines in the spectrum from known elements. And then what we can do is we can see whether those lines occur at the right colors, at the colors where they occur on Earth in a laboratory, or if they're shifted away from that particular wavelength. And that shift is like the shift in the pitch of the sound of a moving car. It's Doppler shift. And so in other words, that shift knows something about the velocities of the hydrogen clouds that are emitting those lines. So in other words, Rubin and Ford set out to measure precisely how spiral galaxies like Andromeda are rotating around their centers. And so I want to just take a step back for just a second, and I'll go through formulas in a moment here. But at this point in time, it was about 40 years since we've discovered that galaxies even exist, that those smudges in the night sky that we see are actually immense collections of hundreds of billions of stars and lots of gas swirling around the common center of gravity. And at that point, people thought, okay, it's the mutual gravity of these things, of this collection of material that we see that holds them together. So Rubin and Ford measured what we now call redshift, Z, so the shift away from the from the wavelength at which the light should have been emitted to some other observed frequency. Again, shift in pitch of the light, if you wish. And so for measurement of the redshift, you can infer the relative velocity of these particular points away or towards the observer. Okay, so if the Disky galaxy is rotating like this, these bits will be going towards you, and these bits on the other end will be going away from you. So those that are going away from you will be shifted red, and those that are coming towards you will be shifted blue. And if you look at this galaxy, even by eye, you can tell, okay, most of the stuff is concentrated in the middle, right? And as you go towards the edge of the disk, the density of the material drops off until you can no longer even see the disk. So what was revolutionary about the spectrograph was that they were, for the first time, able to actually resolve the different points of disk far away from the galactic center. And so what they expected to see is, okay, if we knew Newtonian dynamics holds, if you measure the density, if you infer the density from just how much light there is, if light, in other words, tracks material, then once you hit the edge of the disk, somewhere around here, just by naked eye, right? You should start your rotational velocity should start to drop off as one of the square root of the distance from the center, right? So in other words, once you start to move away from the gravitating material, you should move slower. You should be moving slower and slower. Otherwise, you would break free away from the gravitational pull of this galaxy. So that was the expectation. And this is my attempt to sketch it without having to use the chalk, although I realize I will have to use the chalk in one point in this lecture. So once you hit the edge of the galaxy at about 8 kiloparsecs, and I'm just going to give you a definition of a parsec really quickly. You guys all know what parsec is, right? No? Okay. So parsec is about 3 light years, roughly. Okay. So when I say kiloparsec is thousands of light years, just for scale. So once I hit the edge at about 8 kiloparsecs, by the way, that's roughly the radius of the Milky Way as well, I should start to see the rotational velocity dropping off. What they saw instead was this. Okay? So these are the actual data points for Ford and Rubin data set. And if you go and follow this curve along, here you get like a little uncomfortable. But as you move to the right, you get really uncomfortable. These data points look nothing like the expected Newtonian motion. Okay? So they puzzled over this. They didn't really like it when they saw it for the first time, because what this curve implied is that somehow the material that we see is not all that there is. Stuff out here on the outskirts of this galaxy was flying so fast around the galactic center that it should not have been bound gravitationally to the galaxy. So these are known now as flat rotation curves of Disky galaxies. It turns out that if you want to make all of these points, all of this hydrogen that's emitting, bound to the galaxy, you would need to somehow pack 10 times more mass into it than there should be, given the amount of stars that we see in gas. Yes?
So the left half of the prediction is pretty accurate with the measurements, right?
Sorry, the what?
The first half, before 8 parsecs.
Before 8 parsecs, yeah, so this is my sketch of the theory. The point was the trend. I wanted to illustrate the trend, not necessarily to show you the exact fit.
Oh, okay.
Does that make sense? So yes, within the first bit, within the inner regions of the galaxy, within a few parsecs, the prediction very much agrees with what we see, with what we see the rotations to be. And the prediction comes from how much light we see there, and some basic understanding of, how bright the normal matter is, the stars and gas and so forth.
There is another explanation, isn't there? These things could come from externally and just at this moment in cosmological time, they appear part of the galaxy and then they disappear and they are whizzing away.
Absolutely, totally fair. So let me show you a bit more data. So what then Rubin and Ford did a few years later, they collected data from basically every disky galaxy that they could find. And in a sample of something like 10 different galaxies, some of which are shown here, they saw this exact same trend, right? So, if you wish, some of you, I think, do Bayesian analysis, Occam's razor, right? Yes, you're absolutely right. We could be seeing a very special moment in cosmic history, and something may have conspired to just look like the galaxies are spinning too fast, but it's happening all around us in every single galaxy we can measure. And this data set grew since. So in other words, from 1978, the astronomy community at large accepted that galaxies are only a little bit normal matter and mostly something else. So this was then called dark matter, and there's been a lot of searches trying to understand, well, maybe it's cold gas that we just can't see. Maybe it's, some other particles in the standard model of particles that we love and understand from particle physics. So I want to show you really quickly, fast forward to today, all this evidence across the scales and across the cosmic time now points to that exact same picture, to that exact same figure, that cosmologically, there's about 6 times, not exactly 10 times, because galaxies are very concentrated, special places in our universe, but there's about 6 times more matter in our universe than normal stuff, okay, normal particles.
What is the definition of matter?
Good. That is exactly the question to ask. So the definition of matter for this purpose, and I'll show you in a few slides the math behind all of this, is something that gravitates in the way that we know and understand it from Newtonian mechanics and also general relativity more generally. But simply put, cosmologically, it is material that as you stretch the universe, its density drops as 1 over volume. Okay, that is matter. So it should form structure in the way that we can understand, again, through general relativity and Newtonian mechanics, and it should dilute as our universe expands. Okay, radiation dilutes faster, and I'll show you that in a second. And then we also know that there's this thing, dark energy, which I will not talk about at all in this talk, which is actually now the dominant component in our universe, which does not dilute. So it acts as energy of the vacuum. All right, but we looked at dynamics of galaxies. Every single galaxy we can see. Some of them are even more dark matter dominated than Andromeda. Some of them are mostly dark matter and just a sprinkling of stars on top of them. We looked at cosmic microwave background radiation, which is, if you look at any direction in the sky, you can see this radio hum at about 200 gigahertz frequency, so like millimeter wavelengths. And this hum is the very, very old heat bath from the Big Bang that still, envelops our universe. And when you measure it, the details of how hot, how intense it is in different directions will differ in a universe that has only 15% of matter, and in a universe that has all of the matter that we infer there are from galaxies. So in other words, a snapshot, a baby picture of our young universe, when the universe was only about 380,000 years old, it's now about 13.7 billion years old, that baby picture will look dramatically different if there was no more matter than meets, the eye. Moreover, that picture would look dramatically different if that matter interacted in any of the ways that we know and understand in particle physics. Mind you, we do know that normal matter scatters photons, right? So if you put more regular matter in the universe, more protons, more electrons, that messes up that original picture of our very young universe. We also now understand that here's a snapshot from one of the most massive galaxy surveys in our universe. So this is a very weird projection where we are in the center here. The slices are missing because we avoided looking through the disk of our own galaxy. So we mapped the sky only in part. And every dot that you saw, if you go away from the center, you're going up in redshift, in other words, in distance. scale, farther and farther into the universe and earlier in time. And every point represents a single galaxy. So what you see here is that web-like structure starting to emerge because galaxies that are made of stars and gas trace the distribution of all of the matter in the universe. This picture would look dramatically different. Most of these galaxies would never form if there wasn't 6 times more matter in our universe than there is.
What do colors represent in the second picture?
What do colors represent? I think the type of galaxy, there's various weird names depending on how they, what emission lines they have and stuff like that. So it's just different data sets. And then I want to just highlight this last one here, which is that, according to general relativity, matter, bends space-time, put simply, and therefore it alters the way light propagates in the universe. So in other words, massive objects lens light coming around them. And this gravitational lensing effect, much like optical lensing, distorts images of galaxies in our universe. And that is a very different way to probe how much material there is than looking at how quickly our galaxy is spinning or how does the baby picture of the universe looks like. And all of that testifies to that exact same number that matches perfectly amongst these different data sets, that our universe seems to have 6 times more matter than the particles we know. I won't talk about the composition of the universe, but that's yet another line. All right, so this is where we are in 2024. And now I want to take a step back and give you just a little bit of the meat behind it. For mathematicians, this is fun. This is the bit that I never show in a colloquium. But I take it this is okay because I'm in this room. So this is the last picture for this part of the term. Okay, so cosmology 100. Our universe is the same everywhere. We used to assume this since Copernicus and Galileo. Now we know it. Because when we look at that baby picture of our universe from a fraction of its current age, these different colors represent different temperatures in different positions in the sky. By the way, this is called a Mulwade projection. Maybe some of you know the old maps of the Earth are in that same projection. So that's the entire sky, the full 40,000 radians. And the different colors are different by 1 part in 100,000 in terms of the temperature. So our universe is unreasonably uniform, crazy uniform. This bit of our universe that's over here and that bit over there never were in causal contact. You rewind the expansion and they never should have known about each other. And yet somehow it's extremely, extremely uniform.
So these are the spatial projection of the universe.
That's right. This is the directions in the sky, just like a map of the Earth, right? And then put that, unravel a sphere and put it on a piece of paper, right? So galactic north is up here, galactic south is here, and this point are the same. They meet around. And then do the rest in your head. Similarly, when we look at galaxies, we see the same picture. There isn't a direction in the sky where there's more galaxies, statistically speaking, than in another direction. And moreover, when we look at distant galaxies, each and every one of them is red in the sense that the light from these galaxies is shifted towards lower pitch because galaxies are moving away from us unless they're gravitationally bound to us, and don't look too close. Look far away enough and you will see the expansion of the universe through the shift in the light of all the galaxies that we can see. So our universe is homogeneous, isotropic, and expanding. These are the key ingredients of modern cosmology. And then the other key ingredient is Einstein's field equations. Right? So on the left-hand side, you have something that describes the geometry of the universe. And if one of you is going like this, oh good, now I'm not gonna derive anything, but I will describe it. So on the left is the geometry of the universe. You have your metric right there. And on the right is a stress energy tensor. So that's your content of the universe. So very simply, you're connecting the content of the universe to how the universe is, expanding and what its geometry is. And if you apply homogeneity and isotropy, you put some additional constraints into the system. you arrive to something that's at the heart of the science of cosmology, and that's the Friedmann equation, which describes the expansion of the universe versus the energy density content of the universe. This is a gravitational constant. Rho is everything that there is, matter and radiation and dark energy, everything in here. And the Hubble parameter is defined in this way. Dot is the derivative with respect to time. A would be the scale factor. And here comes the only equation that I'm going to write on the board, which I forgot to put on my slides. I do love that you guys have blackboards. Much appreciated. So the scale factor of the universe tells you how much the universe is stretched or squashed with respect to some reference. Okay, so that's what tells you also how quickly it's changing in size. And redshift is that same redshift that we talked about when we talked about the rotation of galaxies. Cosmologists love to use redshift for everything. We use it as a measure of distance in the universe because the farther you are away from me, the faster you will move from me. And I can make a prediction for how shifted towards the red your light should be if you're a galaxy. Okay. Okay, so this is the full mathematics behind it. But then comes the question of, okay, so what's inside of the universe? So back to your question about what is matter, right? Right now, we know from tracking exactly how our universe expands throughout its history. We look at objects throughout the history of the universe, and we measure how fast they're moving away from us as a function of redshift, as a function of distance. And from that measurement, we can tweak the different amounts of the things that go into the right-hand side of that Einstein equation, of that Friedmann equation. Okay, and these are the main players. Normal matter, which scales as 1 plus redshift cubed, which is to say, again, remember, redshift goes as inverse of the scale factor. So that's your length scale. So that's 1 over volume right there. Radiation, which is right now in our universe cosmologically relevant, are photons and neutrino particles, which are super interesting and very interesting to study with cosmological probes, but I won't have time to cover them today. But those guys are redshifting. They're diluting even faster because their wavelength matters. So their number densities are dropping as volume expands, but also their wavelengths are extending as the universe is stretching. And so you have Doppler shift in addition to the drop in the number density. So the radiation drops as 1 plus redshift to the 4th power, and then dark energy, the energy density is constant. So this is a component that starts off unimportant in the early universe. And when everything else dilutes, that's the guy that wins. And that's the guy that dominates our universe right now.
So is there some presumption that total matter is conserved or something like that?
There's no presumption about total matter is conserved. You can pour one component into another. There's not necessarily conservation of energy, right?
No, I mean, if you combine all of this.
Yeah, so what there is what I didn't tell you about is that we're not only trying to figure out in what proportions do these things occur in our universe, we're also asking the question of, is our universe flat or curved? And that too is a free parameter when you're analyzing your data. It turns out our universe is flat as far as we can tell. So that in a sense gives you the total sum of all of these components. The total number is related to the curvature of the universe.
What if there were a source somewhere just creating new energy, new matter or something?
Like just like Rho popping out of nowhere,
Yeah.
rather than pouring from one to the other. Yeah, that would be outside the realm of general relativity. You can do that, but you have to figure out how to do that in a way that's consistent with what we know about physics.
Okay, so there is a presumption.
Yes, absolutely. Yeah. All right, so those are the pillars of modern cosmology. And what we now know, what comes out of measuring that expansion rate, essentially, I'm simplifying things just a little bit here, but basically by measuring this expansion rate, we infer this picture here, this pie chart of the content of our universe. And then we can infer it in all these other ways that I mentioned before. But now we know that about a third of the universe is dark matter plus normal matter, and then the rest is dark energy. That is the modern, the standard model of modern cosmology that we call lambda CDM, where lambda stands for dark energy, and CDM stands for cold dark matter, and I'll come to that in a bit. Okay. But I want to just very quickly mention that, as you might imagine, as you rewind the movie back to the beginning, that pie chart is different at different points in cosmic history, right? The stuff that redshifts fast, like radiation, will dominate at early times. So when the universe was in the process, minutes after the Big Bang, of forming nuclei that we see today, that make up all of normal matter, it was actually dominated by radiation. And a solid third of our universe was those neutrino particles that I mentioned before, which you now really try hard to study in lab experiments and also in cosmological experiments. All right, so the last ingredient is, that was the picture so far that I painted was just that of background cosmology. Well, how does the universe behave as a whole? But the universe, as I mentioned before, that baby picture has those tiny perturbations in density to it. And those tiny perturbations were tiny early on, and they evolved over time. And we use the usual Boltzmann system of equations, linearized. So assuming that the density perturbations marked with deltas here and velocity perturbations were all very small. We know that this is so because when we look at the CMB, it testifies to this picture, the cosmic microwave background. So we can throw away any terms that are higher order in these small quantities. And I won't parse this out completely for you, but what I want to get your attention to is chi here typically stands for dark matter, B stands for baryons. Cosmologists have this weird habit to call all normal particles baryons. And we disagree with particle physicists because baryons are supposed to be heavy particles. Well, we even call electrons baryons, it's all baryons. If it's not dark matter, it's baryons. But how do you know which one's which? So you here have the expansion component, but then you also have these R terms. The R here basically talks about, actually, I'm sorry, this R right here talks about how dark matter may communicate with baryons and the other way around. So in other words, these terms right here are describing scattering interactions between dark matter and baryonic particles, okay? In the standard model of cosmology, we usually assume that these are zero. Dark matter doesn't talk very much to baryons at all. Otherwise, we would have seen evidence of that already. But it would be really nice if we uncovered some evidence of this kind of cross-communication between different domains in our universe. And this is one of the things that we're focusing on. And I'll come back to that in a minute. The density field starts with tiny fluctuations, and they're Gaussian, thank goodness. So we can assume that when we break things down into Fourier space, different Fourier modes are not cross-correlated with each other, which makes the system really easy to solve, K by K, wave number by wave number. Okay, so linear Boltzmann equations are easy to solve. Problem arises when we start to have those perturbations give birth to galaxies and objects that are no longer small fluctuation in the density, but actually massive gravitationally bound objects. And that happens over time. So we have different ways of dealing with late universe than this early linear universe. All right, and so here's the main player on the scene when we try to quantify the effects of new physics on cosmological observables. And that is the power spectrum of matter in our universe. So what you should imagine here on the horizontal axis is length scale, where you have the wave number k. So small is on the right, big is on the left. Okay. And on the vertical axis is the variance of the density field in Fourier space. Okay? So in other words, take a sphere of a given fixed size, okay, and place it somewhere in the universe, compute the average density in there, and then move it to the next position, compute the average density there, move it to the next position, and do so for every location in the universe. Find the variance of that distribution. We said it's Gaussian, so that's really nice. It's centered on 0. But find the variance of that distribution and do that in Fourier space. That's what the height of this curve is, okay? So the higher this curve is, the more structured the universe is on that particular scale, okay? Now, we observe a variety of things in our universe. We observe hydrogen gas, we observe small galaxies, we observe large galaxies. We look at things like stellar streams in the Milky Way. We can see how much galaxies are clustering, lumping together, and so forth. So in other words, we have a variety of visible tracers of matter in the universe. So we can use those observations to convert that picture and put the data points on what this linear matter power spectrum should look like at different scales. And then we get the theoretical prediction for the matter power spectrum by solving those linear Boltzmann equations that I showed you before. So we involve those perturbations under gravitational force, and we can compute what that curve should look like given the amount of dark matter, the amount of normal matter, the amount of dark energy, and given how these things interact with each other or not. And so we can tweak our cosmology, we can tweak the microphysics and get the curve under different conditions. And the one shown here is the current best fit to the data points that we have from various observations. Okay, so here's the take home. More power in the power spectrum means a lumpier universe on that scale. So that's what I would like you to remember for the coming part. All right, so we see the universe with these fluctuations. We evolve them, by solving those linear equations for as long as we can. But then we have to give the rest of the job to the computer, usually a supercomputer, and tell it how gravity works, and let it figure out the rest. So here's an initial condition in a very early universe. And here's one of the computer simulations that evolves this universe forward using numerical approaches. And what you see here is the distribution in dark matter. And where the darkest regions are, that's where most of the density is. Those fainter regions, gray regions, are big voids in the web of structure in our universe. And what I want you to note is, so this background is expanding, but gravity is acting and collecting, more material to where there was a little bit more material to begin with. And then at the very end, this simulation zooms in on one particular clump of dark matter that was chosen in this case, and now we're just going around it. The universe is not spinning, we're just moving the camera around. It's chosen to resemble very much our own Milky Way galaxy. Okay? And it resembles our Milky Way galaxy by the total mass it acquired to the present day in this numerical simulation, and also by the fact that it has these two little companions to it. So our galaxy has large and small Magellanic Clouds. These are mini galaxies, dwarf galaxies that go around it. So one take home from this that I want you to note is that where there's more dark matter, that's where baryons collect as well. That's where galaxies light up, okay? So in a sense, we have a very biased tracer of this entire underlying picture. Yes.
Is this, are these simulations very sensitive to initial conditions?
Yes, they in fact are, yeah.
So do you get any special structures that you see, special large scale structures that you see then when you do these?
Yeah, so if you change the initial conditions, you end up messing with the universe. So what we do is we put the right amounts of dark matter baryons and so forth In other words, we use the observations that we have to constrain those initial conditions to something that should agree with observations at the end of the day. But in detail, we can mess with microphysics of particles in those initial conditions. And that's actually exactly where I'm going. So we do that as well. And then we can ask a question of what can I do to microphysics before I destroy the galaxies completely in this universe? Okay, so these are our tools. But in summary of the second part, our universe will look very different depending on what the microphysics is, which is a weird thing to say because the universe is 20 gigaparsecs across. What is that, 20 billions of light years across. Did I say that correctly? 10 to the 9? That's a billion, right? Something like that. Rewind back this to the first few minutes after the Big Bang, and you get these 20 gigaparsecs packed into a ball this big. Okay? And you go another fraction, this fraction of a second back in time, and that entire thing that's about a meter across is smaller than the size of the smallest fundamental particle today. So you see, when we mess with microphysics, when we mess with particle physics, we change the universe on large scales. And we can see that thanks to the expansion of the universe that's been happening for 13.7 billion years.
So what you mean is messing with the particle physics right before Big Bang and then let the Big Bang
Right
happen?
after. We don't have a
Everything's
before.
after.
Right after
No,
the
what
Big
I mean is it like right after Big Bang, or if you are able to mess with the physics right now, it'll still destroy galaxies
Yeah,
a
so
day later?
everything is cumulative. If you think about it, if I tell you particles interact in a certain way right now at these energies, if I'm a particle physicist, I will write a Lagrangian that describes that interaction, but then I know what it should do at any other energy, right? Like if you have a complete theory that describes the interactions, that theory should work at any energy. So if you tell me what's happening today, I should be able to tell you what happens when the universe was a lot hotter and denser and so forth. Unless something else happens at a different energy scale, but then you're putting new knobs into your model, right? So you pay the price. Once you specify the physics at one energy scale, if you want to be complete, you pay the price of telling me what happens at any point in cosmic history. So I can look for it, maybe where the effects are most prominent. And that's exactly what we do. So I can tweak things early on, or I can tweak them later on if I make up a theory that doesn't do much at high energies, but it does do at low energies. And we do that as well. Okay, so we can ask really fundamental questions about the nature, of space-time and matter in cosmology. This is what we do. We really do fundamental physics using our universe as a laboratory. So we ask questions like, what forces govern our universe? We know of the four, but then, there's this whole dark matter and dark energy thing, which could be its own sectors of new physics that we don't yet understand. We ask questions like, how did structure form in detail on all scales, like what you saw in those simulations? And finally, what is the nature of matter and the constituents of our universe? So I'll focus on that last one for the last bit of this talk. Okay, so that's my bit about equations. Now I want to pivot, and I'm going to show you two examples of how we play this game over in the astrophysics group, and how we try to turn this story into discoveries of new fundamental physics. So different fields operate in a different way. In astrophysics, we very much have our students and junior folks like postdocs lead the work that we do. So I have to give a shout out to this amazing group of people. Most of the plots that you will see, most of the things that I have to show you today have been contributed to by different subsets of these people here. And I particularly give a shout out to our postdocs who have now moved just at the beginning of this semester to new positions. And one of them is now new faculty at San Diego, UC San Diego. All right, the data that we that we use to study our universe typically come from observations from space telescopes and ground-based telescopes. This one's called the Vera Observatory in honor of the astronomer that I started to talk with. But the purpose of all of these instruments is to survey our universe at various wavelengths and at various points in cosmic history and understand what structure looks like and what the dynamics of the universe looks like throughout cosmic history. So they each have their own special regions in that parameter space that they can explore. And in astronomy, the data is usually released publicly. So I do participate in a few of these collaborations as a collaboration member, but I'm not representing any of them right now because most of my work really relies on digging deep into the data that's publicly available to us to explore. And this slide here is just meant to give you a recoil of like, oh my God, theorists have so many ideas for what dark matter should be. And this is just meant to say, so all of these names are different ideas for how dark matter should fit within the framework of particle physics. And what I want you to take from this is that this is a wide open field. We really don't know. There's a lot of things that could fit and are motivated in various different ways. Some of these ideas solve other problems in particle physics. Some of these ideas are just plain interesting phenomenologically, but there's a lot of ideas there. So there's a lot of possibilities to kind of plow through and check whether they actually make sense and understand what their cosmological consequences are. And that's where we come in. But all of them do something to that matter power spectrum that I showed you before. Now I'm normalizing it in a slightly different way, but this is that same quantity that tells you about the clumpiness of the universe on different scales. And what I want you to take from this is that, check it out, all of the data that I showed you before really is clustered on large scales. We really know how things are distributed on large scales. We're just starting to learn what's happening on small scales, on subgalactic scales. But that's exactly where these different theories, these different dark matter phenomenologies start to differ from each other and from that standard called dark matter cosmology. All right. So what can dark matter do? Dark matter can alter the distribution of the universe in various different ways. If dark matter is cold, it just means, in cosmology, it just means that it interacts only gravitationally and has no pressure. Okay, it's a component that's pressureless. If it is warm, it means it's a particle that is produced with a significant free streaming velocity. So it has the capacity to escape gravitational potential wells for a good portion of cosmic history. So it does not clump as easily. It has some pressure to it. If dark matter annihilates into, let's say, radiation, okay, photons or some dark radiation, this is a thing, by the way, in cosmology, some new particles that are massless, like our own photon, that'll alter the expansion history because exactly what components are relevant cosmologically in our universe decides how quickly our universe expands. And then we have really funky candidates like fuzzy dark matter, which is a bosonic particle with a de Broglie wavelength that's the size of a galaxy. Okay, so this is something where you should see quantum effects on galactic scales. So you can do that kind of thing as well. And it's really phenomenologically really cool model to explore. The one that I want to focus on for the last few minutes is interacting dark matter. So this is dark matter that just simply scatters with normal matter. So it communicates with normal matter. It can't do so very much, otherwise we would have seen the effects of this. But you can ask a question of how much interaction can there be with the data that we see being, the theory of the interactions being consistent with the data that we see.
Was that the R sub?
Yes, that was R sub chi. That's right. Thank you for noting that. Okay, so my example number one is interacting dark matter. And I'm an astronomer, especially for this bit, which means that I take a step back and I zoom out. And to me, interactions are Feynman diagram to me can be something very simple like this. You have dark matter and standard model particles, normal matter coming in, and the same two particles are coming out. So there's some elastic scattering happening. So when we ask about interactions, we don't actually have to specify the full Lagrangian in order to ask whether there was some momentum and heat exchange between the associated fluids. And that's what we can do. So I can say, okay, let me put this RCI term, this momentum exchange term, into my Boltzmann equations and ask a question of what happens to the universe if dark matter scatters like billiard balls, velocity-independent elastic scattering with baryons. Now, baryons, normal matter, they talk to radiation through electromagnetism. So they're hot for most of the cosmic history. They're not cold. They have pressure. So that means that if you put dark matter and baryons into thermal contact, you pay a price by heating up dark matter and giving it maybe enough energy to start to not clump as well as in the universe where you have no interactions whatsoever.
What's N?
N is a power law index that you can, that is basically amounts to the choice of the interaction operator that you want to produce this interaction. Okay, so if you want velocity-dependent scattering, you can have it. There's plenty of operators to low order momentum transfer that will produce, velocity-dependent scattering cross-section, momentum transfer cross-section. All right. So I mentioned before that the height in the power spectrum denotes how clumpy the universe is on a particular scale. So I'm going to ask you a question, and I see that I'm running out of time, so this is going to be, I'll cut it a little bit short. I'm going to ask you a question of which simulation here, this is a simulation that zoomed in on a halo of dark matter that has a lot of substructure, a lot of subclumps. Which one features more dark matter baryon interactions? So let's see. Who would vote A? You guys gotta vote. You gotta take at least an attempt.
Vote A.
Who would vote B? Oh, good. So you are following. That's awesome. All right. So you erase structure when you transfer momentum and energy between dark matter and baryons. Okay, you pay a price because baryons are hot. They won't cluster as easily as in cold dark matter scenarios. So that's just a visual of what actually happens quantitatively. If I show you again the power spectrum, but this time I normalize to standard cosmology where you have no interactions, this is the kind of cutoff that you will see in the matter power spectrum. So in other words, to the left, on small scale, structure is suppressed, just like you saw in that simulation. Okay, so you don't have as many little clumps. On the right, structure is intact. The more interactions you have, the more you push this cutoff towards larger scales. The farther your particles exchange momentum and heat, and the more smooth your universe is on larger scales. I'm sorry about that. Okay, so the cross-section for the interaction is the parameter that I'm interested in. And now I take in the data, and what I can say is that our galaxy, this is actually Andromeda, but our own galaxy looks very similar, has a whole bunch of little galaxies swirling around it. We know of something like 60 of them right now. And the smallest ones live in halos, in blobs of dark matter that are about 10 to the 8 solar masses big. And so we know that structure on scales that correspond to that mass scale is intact. So in other words, the presence of structure in our own Milky Way forbids interactions from being too strong. Otherwise, we would have erased those little galaxies from existence. And so this approach has led to some of the strongest bounds available today on dark matter particle masses that are sub-proton mass. So GeV is a proton mass. And then the vertical axis is the interaction cross-section. So the bounds that we had previously from cosmic microwave background are the green regions here. And applying this kind of approach of asking a question of how much can we turn on the interaction before we destroy the seeds that will one one day grow into what we see as dwarf galaxies around the Milky Way, we were able to exclude several orders of magnitude deeper in the cross-section. So all the shaded regions are disallowed now by this analysis. All right, I'm going to fast forward to my conclusions and skip over straight to part 4. So where are we going in the future? You can ask me about second example if you're interested after the talk. Susan is giving me the looks. I'm going to rush through. So where are we headed in the future? So what I showed you so far is a very analytical approach to asking this question of what can dark matter do and still stay consistent with observations that we have right now. However, one of the big challenges that we have is creating a way to actually make detailed predictions of what structure in the universe looks like in these varieties of different cosmologies, where dark matter could be warm, or it could be fuzzy and have a large Lippershey wavelength, or it could be interacting with normal matter. So the way that we approach this is by creating the very first suite of cosmological zoom-in simulations that have those initial conditions that are beyond cold dark matter scenarios. So we've just ran something like 72 different zoom-ins where we started off with a simulation of the universe on hundreds of megaparsec scales. We found the galaxies that look like our own Milky Way, that little guy there, and then we resimulated them at very high resolution. So here is a CDM simulation in the standard model. Here's a change in the initial condition leading to the suppression of structure. And we're now in the process of analyzing those simulations and understanding what does the Milky Way look like in detail in these different fundamental physics scenarios. With these new approaches and with the data that we will have coming from new surveys like that done by the Vera Rubin Observatory, we will push these kinds of exclusion curves by 3 to 5 orders of magnitude deeper into this parameter space. So this is a room presumably full of people who do math. If you were doing a lab experiment, trying to detect new particles, and you saw something that goes down in cross-section by orders of magnitude, your mind would go like tens of billions of dollars in terms of lab experiment development. So this is a huge step that basically opens up a big new space, big new parameter space for discoveries. And hopefully, some years from now, we're not going to show you bounds, but maybe we're going to start to show you some signals of new physics. All right, I will stop there and leave my summary slide up. Thank you all for your attention.
Questions or comments? Sava?
So going back to the simulation / animation where camera was rotating around a fixed galaxy that looked like Milky Way.
Yeah.
And then it was bright in the middle but dark on the surroundings, meaning that like there's, if I understand correctly, there's a dark matter concentration around the galaxy.
That's right. So
Do we know anything like that on the scale of star systems?
on the scale of star systems, so dark matter component is so what you should think of is a solid sphere with a density profile that peaks in the middle. Does that make sense when I say it that way? So dense thing that's like dropping off as you go towards the outskirts. But baryons, normal matter, they're really good at sinking to the middle because they can cool, they can let off radiation and really concentrate. So they dominate in the middle. Dark matter starts to dominate outside. But dark matter, as far as we can tell, we can measure. So the point of this program is to understand how it clumps on really small scales. For this reason, that the smaller I go, the more sensitive I am to really small interaction cross sections. and other characteristics of dark matter that I didn't talk about. So we don't yet have a way to ask this question on scales of, like, let's say, star clusters or something like that. These would be really, really small scales where baryons dominate so much that it's very hard to back out whether dark matter has little clumps of that size. That said, there are ways that we're trying to do this, and we can chat more afterwards about that.
Would all of your simulations have looked the same if there was no interaction at all? I mean, I guess like, so you're getting it smaller and smaller, like weaker interactions. But could it be that they just don't interact at all? And
It could be that they don't, yeah, it could be that they don't interact at all. What could also be is that they interact quite a bit, but not all of them. So the standard model of particle physics has a huge number of particles, right? It's not a single particle. The only reason that we've been modeling dark matter as a single particle is because that's the easiest thing to do. This is how far we've gotten right now. So it could, so, you know, I asked my friend who's a particle physics modeler, what does a standard model look like? And her answer was, of course, E&M. It looks like E&M, right? A photon and then an atom, right? And that describes the phenomenology of baryons pretty well. You can play a same game with dark matter and complicate it up just a little bit, and then all of a sudden you end up in a situation where you don't just mess with small scales. You can mess with large scales, but only a little bit, because we have a lot of observations there. But you can pack a lot of interesting physics into a dark sector and not see it if you do it by complicating up your model. So these are the simplest, you know, questions that we've been able to address so far, but there is definitely a lot more to explore, yeah. And it could be that dark matter does not have interactions with normal matter at all. It could be a completely separate sector. It's weird. We've never, you know, like, maybe this is like a circular argument. We've never seen a particle that doesn't, okay.
Yeah, that's the reason you've never seen it.
But you have to forbid it, right? That's kind of the point, is like, if you want to have particles that are born out in the same universe, there's some physics that connects all of that. There's some origin story. Now you have to shut off the communication channel, right? So it's more natural to assume that there is some communication. But if there isn't, there are scenarios where you have like, you know, just like I said, like dark atom and a dark photon. You can imagine something like that. And the channel for communication is really narrow, so we've never seen it. These models are often referred to as like millicharge models. Dark matter could be charged by very slightly under E&M and have its own story inside the dark sector. That too we can explore with cosmological observations, because that too has phenomenology, right? That is interesting and different than cold dark matter.
Other questions or comments?
I have a comment. Actually, when I read the title of the talk, I don't know, I was thinking maybe the talk is going to be about another Big Bang, and then we have a different universe that we are not seeing, that we are not interacting.
Sorry, I tricked you, I said.
Yeah.
There was a wordplay. Did anybody recognize the universe we cannot see? No?
All the light we cannot see.
Thank you.
And obviously, you need money. You even commented on sort of the gaps and the need for data, for experiments, for computations. What are the orders of magnitude of money that you're working in at the moment?
Oh, we are cheap compared to most. So I would consider myself a theorist. The data analysis that I work, okay, data-driven theorist. Okay, so most of my work is data analysis and then coming up, like understanding what are the observable consequences of a model, right? Of an interesting particle physics model. That means that I mostly work, like the biggest expenses are people and then computational power. So we do have to, you know, like we do have to have supercomputer time. but there are a lot of
But it-
additional
You're
resources.
relying on observations.
Yes,
so
you're relying-
telling us-
yes.
Yeah,
You're
absolutely.
using publicly
Yeah, yeah.
available information
Yes.
to cost money.
Yeah, absolutely. We are, but this is the difference between the way astronomy operates and the way that other physics domains operate, is that usually data is mandated to be released to the community. And we're very lucky to also be a part of a collaboration, and we'll have first dibs on some of the data that's coming in, first light this year from the Simons Observatory. So we do things like that. We contribute to collaborations, and that gives us, first access to the data as well. And yes, these are very expensive experiments, but not as LHC and so on.
Yes.
Yeah.
So you can go forward confidently in terms of the Simons Foundation, for example, supporting
Yeah,
what you
they're
do.
big,
Mhm.
they're a big deal in our field. You guys not tired yet?
The light's this dark, I guess.
So there's no chance that even if dark matter is something like 6 out of 7, there's no chance there's an interchange there over time.
Between dark matter and normal matter?
Yeah,
Oh, there
but-
absolutely is.
But
There's-
maintaining the ratio.
Yeah, they're absolutely, maintain but turning like interactions that are converting some one
Converting
particle.
some to,
Yeah,
in
yeah,
the same
so-
proportion.
Yeah, so baryons communicate with radiation. That's a big, that puts a big constraint on how much of them you can. So I haven't talked about the many observations that we have that limit, why do we know that dark matter is a new particle, right? Because if you put 6 times more protons in the early universe, right? Like all of a sudden, all of your matter interacts with radiation, and that changes dramatically everything, right? The composition of the universe, and how elements form, how structure forms, and so forth. That said, there are blind spots as well. There are blind spots where you can do conversions to a small degree, and we do talk about annihilation of dark matter into standard model particles. But these models too are, there are constraints on them, because we can look for effects like that. For example, if you look at a galaxy and it's glowing from its center in, electrons or gamma rays or something like that, that's a sign that something's happening where dark matter is most concentrated. We don't see things like that.
Other questions? Then let's thank Vera for a very interesting talk.